To know the difference between delta G and delta G reaction can be the key step for you to find a solution for a given problem. Delta G reaction represents the Gibbs energy change of one mole reaction at standard conditions, and delta G represents the change of Gibbs energy. Let me use an example to explain why you need to know the difference between the two. It doesn't matter what kind of problem we are given. We always use the same three-step procedure to find a solution for the problem. Summarize, analyze, and work out the details. The first step is to summarize. We need to write down the most important information. There are three different kinds of important information. If you have a chemical reaction, a balanced chemical equation is always the first piece of most important information. The numbers with the units is another type of important information. And the third type of important information is what we are looking for. Let's read the problem together. Octane is the main component of gasoline in your car. When you drive, the octane in your gas tank will react with oxygen. The Gibbs energy released will allow the car to carry you to the destination. Please calculate the Gibbs energy change when 2.51 gram octane reacts with excess oxygen at 298 Kelvin. A balanced chemical equation is provided to us. Therefore, we will write down the balanced chemical equation immediately because we are looking for the Gibbs energy change. So, I will put down the standard Gibbs energy of reaction on the same line as the balanced chemical equation. The standard Gibbs energy of reaction is the Gibbs energy change of one mole reaction at standard conditions. Therefore, I put delta G reaction on the same line as the balanced chemical equation, even if I do not know the value of delta G reaction. The mass of octane is 2.51 grams. I write down the mass of octane below octane under the chemical equation. The Gibbs energy change is what we are looking for. And this Gibbs energy change is from 2.51 gram of octane reacts with excess oxygen. Therefore, I put down delta G on the same line as the mass of octane. The temperature is 298 Kelvin. This temperature does not belong to any other chemicals, so I put T at a different place. Look at what we have. We are provided the information of octane, and we are looking for the change of Gibbs energy. If we know the standard Gibbs energy of reaction, this is almost like a stoichiometry type calculation. Let's recall what we learned from class. What are the different ways to calculate the standard Gibbs energy of reaction? We are provided the standard enthalpy of formation and the standard molar entropy of several chemicals. Let's say if we can find the standard enthalpy of reaction and the standard entropy of reaction, because we all know the temperature, if we can find this one and this one, and then we can find the standard Gibbs energy of reaction. Recall what we have learned in class. The standard enthalpy reaction can be calculated by using the standard enthalpy of formation of the products and the reactants. The equation is N is the corresponding coefficient of the products in the chemical equation. M is the corresponding coefficient of the reactants. We have a similar equation to calculate the standard entropy of reaction. From what we have, it seems this calculation is possible. This is the first step. This is the second step. We plug the standard enthalpy of reaction, the temperature, the standard entropy of reaction. We can find the standard Gibbs energy of reaction. This is step 3. Then we use the standard stoichiometry to calculate delta G. We may need to add another step to convert the mass to moles. This will be step 4. Then we use the stoichiometry to find delta G, the Gibbs energy change. Step 5. Now let me show you the details of each step. Step 1. We will calculate the standard enthalpy of reaction. The standard enthalpy of formation of carbon dioxide gas is negative 393.5 kJ per mole. The coefficient for carbon dioxide gas is 16. We multiply 16 moles. Water liquid is another product. From the table, the standard enthalpy of formation of water liquid is negative 285.83 kJ per mole. The coefficient of water liquid is 18. For octane liquid, the standard enthalpy of formation is negative 252.1 kJ per mole. The coefficient is 2. We find that the standard enthalpy of formation of oxygen gas is missing. But if you remember, the most stable element of oxygen is O2 gas. It has 0 standard enthalpy of formation. It doesn't matter how many moles, it is still 0. The answer is negative 10,936.7 kilojoules. Step 2. We will calculate the standard entropy of reaction. For carbon dioxide gas, the standard molar entropy is 213.6 joule per mole per Kelvin. The coefficient of carbon dioxide gas is 16. For water liquid, the standard molar entropy is 69.91 joule per mole per Kelvin. We have 18 moles. For octane liquid, the standard molar entropy is 361.20 joule per mole per Kelvin. We have 2 moles. For oxygen gas is 205.0 joule per mole per Kelvin. The coefficient of oxygen gas is 25. The unit is joule per Kelvin. After we punch all numbers into the calculator, we get 114 joule per Kelvin. Step 3. We will calculate the standard Gibbs energy of reaction. I rewrite the equation to help me to memorize the equation. The unit of the first term is kilojoules. The unit of the second term is joule. So we have to convert to make sure we have the same unit for both terms. The answer is negative 10,580 7.7 kilojoules. Sorry, this number was wrong. Step 4. We need to convert the mass of octane to moles of octane. We need to calculate the molar mass of octane first. The unit of the molar mass is gram per mole. The last step, we will use the standard stoichiometry calculation technique or skill to convert the moles of octane to the Gibbs energy change. From the chemical reaction, every 2 moles of octane react with excess oxygen. It will have a Gibbs energy change, or we call the standard Gibbs energy of reaction, which is negative 10,587.7 kilojoule. The final answer is negative 116 kilojoules.